Hello, my name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook and
Jupyter notebook.
by the end of this lecture, we will define and train a neural net. And you'll get to see everything that goes on under the hood and exactly sort of how that works on an intuitive level. Now, specifically what I would like to do is I would like to take you through building of micrograd. Now, micrograd is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you'd have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of comment on all the pieces of it. So what is micrograd and why is it interesting? Good. Micrograd is basically an autograd engine. Autograd is short for automatic gradient. And really what it does is it implements backpropagation. Now, backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograd is, I think, best illustrated by an example. So if we just scroll down here, you'll see that micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograd. So this value object will wrap the numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograd and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them to a constant power, you can offset by 1, negate, squash at 0, square, divide by a constant, divide by it, etc. And so we're building out an expression graph with these two inputs A and B, and we're creating an output value of G. And micrograd will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the child nodes of C are A and B, because and it will maintain pointers to A and B value objects. So we'll basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, where we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out. But the big deal is that we can also take this G value object and we can call .backward. And this will basically initialize backpropagation at the node G. And what backpropagation is going to do is it's going to start at G, and it's going to go backwards through that expression graph, and it's going to recursively apply the chain rule from calculus. And what that allows us to do then is we're going to evaluate basically the derivative of G with respect to all the internal nodes like E, D, and C, but also with respect to the inputs A and B. And then we can actually query this derivative of G with respect to A. For example, that's A.grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A.grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. So that's going to tell us about how G will respond if A and B get tweaked a tiny amount in a positive direction. Okay? Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input, and it's a mathematical expression, and the output are your predictions of your neural net or the loss function. We'll see this in a bit. But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions. And then we happen to use that machinery for training of neural networks. Now, one more note I would like to make at this stage is that, as you see here, micrograd is a scalar-valued autograd engine. So it's working on the level of individual scalars like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in a modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really, none of the math changes, and that's done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to micrograd, and you'll see that there's only 2 files here in micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of micrograd. So engine and nn.py. So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code, and that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy-paste in every Jupyter notebook always. And let's define a function, a scalar valued function, f of x, as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20 back. Now, we can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's a quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25. So x is just from -5 to 5. Not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x.
So because it's a square here, that's why you see a parabola in Andrew's mess. It's basically 3 square 9, 27 minus 12, 15 plus 5, 20. That's what we are getting here. So this is the one. We're passing a whole list. Sorry. So for each of the values from -5 to 5, right, with a difference 0.25, it's calculating this value. And we can plot it using
X's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write it out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. it would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what derivative is. Very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus a slightly bump up. You're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, as 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in the positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope because we have to make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer because we're using floating point arithmetic and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6x minus 4. And then we plug in x equals 3. So that's 18 minus 4 is 14. So this is correct.
So h is the very small change that we want to do. F of x plus h is, so it's at 3, right? So we are adding 3 plus h somewhat like here, minus f of x and divided by the change that we are doing. So it's near about 14.
So that's at 3. Now, how about the slope at, say, negative 3? What would you expect for the slope?
So if it is negative 3, right? If we add something, it moves a bit here. So minus 3 plus h, you can say somewhere is like that, which is lower. So the value is going down. So we expect the slope to be negative. You are getting a negative value.
Now, telling the exact value is really hard, but what is the sign of that slope? So at negative 3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3, that's somewhere here, this derivative would be 0. So basically, at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable b that is a function of three scalar inputs, a, b, and c. So a, b, and c are some specific values, three inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c, and think through, again, just the intuition of what this derivative is telling us. So
Sorry, he took it as -3. So now what he is asking is if how d changes, or the amount of change in d if a changes by a small bit. Okay, and everything else remains constant. So we can do that. Let's take a plus equal to h, and let's define h here as well. So h is equal to 0.001, d is equal to the b plus c. Value of d reduced. So it's a negative. So the thing is, if we change a by a small bit, right, the value of t decreases. Why the value of t decreases? Because b itself is a negative. So when you multiply negative with a larger value, because a's value is changing, right, so it is becoming much more negative. As a result, the d's value is reducing. So it means if we increase the value of a, the value of d reduces. That's why the slope is negative.
in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to print, f1, d1 is d1, d2 is d2, and print slope. So the derivative, or slope, here will be, of course, d2 minus d1 divided h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount. And this is then normalized by h to get the slope. So yeah. So if I just run this, we're going to print d1 will be bumped by h. So let's just think through a little bit what d2 will be printed out here. In particular, d1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4? And it's going to tell us the sign of the derivative. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but b is a negative number. So if a is slightly more positive, because b is negative 3, we're actually going to be adding less to d. So you'd actually expect that the value of the function will go down. So let's just see this. Yeah, and so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then will be a negative number because we went down, and then the exact number of slope will be, exact amount of slope is negative 3. And you can also convince yourself that negative 3 is the right answer mathematically and analytically, because if you have a times b plus c and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is negative 3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different slopes. So
So now when we increase the value of b, right, so it became a bit less negative. As a result, this multiplication that came became a less negative. As a result, when we added it to c, right, overall the value was more. So that's why you see a positive value, whereas in the before case, right, we're seeing it as a negative value.
So what is the influence of b on the output to d? So if we bump b by a tiny amount in a positive direction, then because a is positive, we'll be adding more to d, right? So and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be differentiating with respect to b would give us a, and the value of a is 2. So that's also working well.
Yeah, so what he's saying is if we differentiate it with respect to b, right, so it will come as a, whereas c differentiation will be 0, so we will see only a. That's what you are seeing here, the value of 2 coming, which is equal to the value of a.
And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher at the exact same amount that we added to c. And so that tells you that the slope is 1. That will be the rate at which d will increase as we scale C.
This
Okay,
will
so we now have some intuitive sense of what this derivative is telling you about the function, and we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of micrograd. So let me copy paste a skeleton of the first very simple value.
sorry, where is repo? Okay, here it is. Timing, let's remove it.
Object. So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can we can look at its content. And Python will internally use the repr function to return this string. Whoops, like that. So this is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like two values, but we'd like to do a plus b, right? We'd like to add them. So currently you would get an error because Python doesn't know how to add two value objects. So we have to tell it. So here's addition.
Still, we haven't defined grad. So usually the add, it's something like dot underscore add b. So 2 plus minus 2 minus 3 is minus 1.
So you have to basically use these special double underscore methods in Python to define these operators for these objects. So if we call if we use this plus operator, Python will internally call a dot add of b, be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of. So this operator here is just the typical floating point plus addition now. It's not an addition of value objects, and will return a new value. So now a plus b should work, and it should print value of -1, because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So multiply, I think it won't surprise you, will be fairly similar. So instead of add, we're going to be using mul, and then here, of course, we want to do times. And so now we can create a C value object, which will be 10.0, and now we should be able to do a times b. Well, let's just do a times b first. That's value of -6 now. And by the way, I skipped. Over this a little bit. Suppose that I didn't have the repr function here, then it's just that you'll get some kind of an ugly expression. So what repr is doing is it's providing us a way to print out like a nicer looking expression in Python. So we don't just have something cryptic. We actually are, it's value of -6. So this gives us a times, and then this we should now be able to add c to it because we've defined and told the Python how to do mul and add. And so this will basically be equivalent to a dot mul of b, and then this new value object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from before. And I believe we can just pull them manually as well. There we go. So, yeah. Okay, so now what we are missing is the connective issue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason.
So the construction is only tension nothing this
I believe it was efficiency, but this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we are creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case
because of the self and other we got the value this addition, that's why we are passing these to children. The addition happens and this is the newer parent that is found.
is self and other. So those are the children here. So now we can do d dot prev, and we'll see that
Okay, we need to specify it that itself is sufficient. So if we do this and C and do d dot dot underscore prev, sorry, it was a multiplication of these two, that was -6 this one like this one, and the data is 10, then is C as this one. So addition between these two for the children.
the children of the, we now know, are this a value of -6 and value of 10. And this, of course, is the value resulting from a times b. And now the children of every single value, but we don't know what operation created this value. So we need one more element here. Let's call it underscore pop. And by default, this is the empty set for leaves. And then we'll just maintain it here. And now the operation will be just a simple string. And in the case of addition, it's plus. In the case of multiplication, it's times. So now we not just have d.pref, we also have a d.op. And we know that d was produced by an addition of those two values. And so now we have the full mathematical expression, and we're building out this data structure, and we know exactly how each value came to be, by what expression, and from what other values. Now, because these expressions are about to get quite a bit larger, we'd like a way to nicely visualize these expressions that we're building out. So for that, I'm going to copy paste a bunch of slightly scary code that's going to visualize these expression graphs for us. So here's the code, and I'll explain it in a bit. But first, let me just show you what this code does. Basically, what it does is it creates a new function, draw dot, that we can call on some root node, and then it's going to visualize it. So if we call draw dot on b, which is this final value here, that is a times b plus c,
2 घंटे में